Just I was about to say, if at any point you don't want to be heard or you don't want to be in the recording, just put your question in the chat line and I'll try to respond if you don't mind. It's okay. As I said, a lot of this trend on attention models started with this paper, Attention is all you need. And this was published around 7, 8, 10 years ago. And lots of basic concepts of attention. Obviously, again, as anything like AI is incremental work, but came discussed in that paper. I will cover some of the basic concepts came in that paper, and I'll move on how this has now evolved to create language models. Have you seen this video? If you have seen it, then it just defies the purpose. If you haven't seen it, it's a really interesting concept about if it's going to work, is it? Doesn't. What's wrong? Okay. I can't play the video for some reason. My
Can you mouse over it and then click on it?
The reason is I think I'm using a different Word version here compared to my screen. Let me just play it on YouTube. I can do it on YouTube. I should have tried this before. YouTube.com. I think most of the neuroscientists have already seen this. Attention test is called. Greg, is that correct? Yeah.
Oh, there you go.
Oh, no, we will have to watch an advertisement.
You can edit your meta tags page by page.
The instructions are clear, just count. I took a wrong version.
It's the same. That's Jazzy version.
No, I think the original version is much better. How many times they're passing the ball? Did you count how many times they did? Did you see the moon bear? Did you see a bear was walking in the screen? Did you see that? Have a look again. This is an amateur version of it. The professional version actually is really made better. But actually, the first time actually I watched it, I completely missed it. And that's how brain's attention mechanism works, right? Depending on what we are paying our attention, our brain just constantly switches between sort of different sensory parts of the brain. They get involved and process the information we actually paying attention to. For a long time, this was a challenge in machine learning, how we create machine learning models which constantly pay attention to what we want. And what we want often is not very clear or predefined at the beginning of what we are doing, like if you're creating a video processing or image processing. The attention model was one of the really nice efforts. And a lot of it is interesting. It is not really based on real neuroscience. It's not actually based on math. A lot of it actually is information engineering. And for the first time, they created something really, really interesting of how you can create a model which pays attention at different times to different parts of the content, which makes comprehending the content is easier and understandable. If you terminology in attention model comes from information retrieval, I just wanted to clarify, because when you see the terminology, how they refer to it, it just comes from information retrieval. When you're searching for an information, usually you write something in as a keyword in any search engine, in any type of things. When you're looking for information, that's usually we call it a query. And then what happens is you're looking for information, and like in this case, I'm looking for Paddington, and each of these videos, they will have a metadata. Each of this metadata, they have a key. In information retrieval, we refer to this key. They have a key which you're using that key to search for the information. And what you find, for example, if I'm looking for Adventures of Paddington and I find this content, that content information retrieval, we refer to as value. This terminology will now, you will see it. I just wanted to clarify where that comes from. When I say this is a query, this is a key, this is a value, what we mean by it. The value is the content itself. The key is information which is provided. It helps you to find that value. And what you're searching for with it is called a query. And this is used in attention model and across all the computational world in information retrieval. Most of my examples for this will come from with natural language processing, because initially attention models were presented for natural language processing, but a lot of it is applicable if you're using genetic data. You can take your genomic sequences and you can embed them, and I'll come to the embedding, like represent them as a vector, and then sequence of vectors, you can apply attention model. Then and each time you learn how the sequences, they basically join up together or how they appear together. You can take any behavioral data or any like monitoring data we use in our research in UKDRI. You can take that data again, create and look at how the sequences they work. And you can look at natural language processing, and you can assume all the words are coming in an order. They have a temporal order, and the position of them is important, and the context of them when they appear with another word makes the interpretation and meaning of them is sort of clear. For a long time, for decades and decades, information retrieval and people who worked on natural language processing, they have developed different technologies, the different solutions to look at how you can extract from sort of neighboring words or the context of the text to be able to find what is meant by a word. For example, here what I've written, if you read it, here now Paddington has two different meanings. One Paddington refers to the bear, the other Paddington refers to the train station. And obviously by just looking at the neighboring words, in this case, you might be able to find the relation between them. And also I'm referring to jam as traffic jam and or marmalade jam, which Paddington likes. You can see where my examples are a bit stupid, but another thing is, over time, you also want to understand whether a traffic jam is something has a positive sort of implying a positive sentence, or traffic jams are referred to negative things, for example. And these are type of things you want machines to be able to understand themselves by processing the text. Here, you're not giving information to machines to say this is positive or negative. You want them to just constantly, while looking at the text, to understand first jam could have a different meaning, and also to understand how jam around the other words will start providing different meanings. I've realized actually my slide doesn't change. Do you see my slide? Oh, yeah.
Yes, we see it now.
Okay. Yeah, sorry about that. Then attention models will start looking at, designed, as I said, for natural language. They will start looking at sort of a syntax word by word, and at the same time, we'll look at the neighboring words at different locations and try to understand how now the combination of these things could convey a meaning or how they appear together. In principle, before even I move further, you can imagine if you give a large number of this text and you create a model which pays attention to each point to each of these words, you can start creating a predictive understanding of how the words co-occur together. For example, Paddington most of the time appears with station, or Paddington with bear, but Paddington doesn't appear with elephant. Then if you're creating something like ChatGPT, probabilistically, if somebody wrote Paddington, you will suggest Paddington Bear or Paddington Station. And bear with me how now you will decide whether you should put the next word as a station or Paddington as a bear. But for now, you can see just by looking at how they co-occur together, you can start creating a probabilistic model. Natural language becomes a little more complicated. This is a communication Rhiannon and Ivy had when we were organizing for this. And she said, I booked the rooms from 9 to 11. And I said, I cannot make 9 to 11. The earliest I can get here will be 10 o'clock. She wrote back and I said, I had to read it very, very carefully a few times to understand you're referring to the time. I'm referring to the date. Again, you can see the complexity of natural language. It adds a lot is much more complicated to process that. And that's sometimes, again, I'm projecting what I'm going to say future, but start building this. Even you create very large complex models, still unpredictability of it is a lot. In human language and how human brain perceives the information is still there's a sort of a different form of intelligence, which machine intelligence still will struggle to find that. In this case, for example, actually for machine, it will be equally very, very difficult to understand as 9 to 11 is whether the date or is the time we are referring to. That's also now, if you look at if you have used ChatGPT, you will see sometimes it gives you very, very stupid responses. And that comes from the unpredictability of human mind and human language. But generally, to take the visual cortex and brain as an example, if you walk in a street like this in Hong Kong, it's easily you can find the shop you're looking for. Our brain is just triggered to the signs we are interested in and constantly filters other information.
Lights are not progressing, Payam, again.
I'll keep an eye. Sorry about that. Let me see. It's always is one slide behind, and I don't know why.
Got it.
Okay. Sorry. I'll keep an eye on it. And when you're searching for information, if you look at it, sorry, I'm sharing my slides on my tablet, and if this continues, I'll stop and just use my desktop machine. Just let me. It's becoming very annoying. All right.
It's
So
it's super strange. Yeah.
It's,
Now we're back on the like.
Yeah.
forward.
yeah. Okay.
well, maybe this is a really long delay.
If you're looking at, I think there's something with problem with the Wi-Fi. Probably this connector, I should have checked it. If you're looking at this picture, at any point of time, depending on what you're looking for, your brain constantly scans this image. At some point, you're looking at the umbrella. At some point, you're looking at the text. At some point, you're looking at the bear. And I moved this slide. What color was the chimney? Was any cloud? Was there any cloud? You get the attention. Self-attention models, what they try to do, they create an unsupervised model. By the way, the chimney was white and there were some clouds, yes, in the background. With the risk of my slide might move. Self-attention models, they create an unsupervised sort of learning paradigm, constantly tell the learner, the trainer, constantly to focus at different parts and constantly change this focus. And I'll show examples and I'll tell exactly what you mean. And then while you're processing a content, you're constantly paying attention to all different segments and all different parts. And then now how you can use that to create a generative sort of aspect of it, and then look at while you have paid attention to how different things co-occur to each other. And each point, if I query any fragment of it, any part of it, you have already paid attention to what other things appear together. This a bit has changed. Remember, a lot of machine learning was focused on a very specific things. For example, learn faces, learn, I don't know, colors, learn shapes, learn edges. Here you're basically converting your content to little mosaics, fragments in natural language processing to words. And you're telling model at any point, pay attention to every single word at a time, make that word as your focus point, and then look at what co-occurs with it and move to the next word, the next word. And that concept is called self-attention. That's where it comes from. The whole attention model is based on a concept called self-attention. If you take a standard neural network, if you don't like the math, just ignore it because it's just people ask me to provide math. But if you take a normal neural network, what happens is you have a series of inputs. Your inputs are a series of, like a vector. You feed that to your neural network, and your neural network has just some weights. Here is shown as omega, applies your weights to your input, which is shown as X here, and adds as a bias. This is just a standard sort of, let's say, single layer, multi-layer perceptron network. And then there is a training process which you learn those weights. And I'll come back to the training process later on for this. But for now, assume we start from random weights, and we multiply our input to a series of random weights, and we add them a bias, and then feed it to what we call it an activation function. And then by that, we get a result, and then we calculate the gradients or whatever you're using it to train our network. And eventually, after a few iterations, we'll learn the new weights. In self-attention, we change this paradigm slightly. We still have our sort of inputs. These are our inputs, which are represented as vector. And we have an omega. We still apply a fully connected neural network, a fully connected network to our values. We have an omega weight for it. And we have a biases. Up to here is very, very simple and very similar to the concept of fully connected neural network. Take it as like a single layer fully connected multi-layer, single layer perceptron model. And then what we do, we get these results, we call them as our values. And then what we do, we get the values, and then each of these values, let's say I had 3 inputs. I had a fully connected neural network. I just drew it as a box, and I get again 3 values. And then each of these 3 values, they now will have sort of a weight, which is called their attention weight. They will pay attention to the other one. Let's say if it was, I don't know, Paddington Bear N, each of them now will have a weight which will pay attention to the other one. I will have better graphs to show this. In reality, what happens is it's not readable. In reality, what you do, you take your input and imagine in natural language, each of these X's are one word. If you're taking genomic data, each of this will be like a genome sequence, depending. If you're taking behavioral data, this would be data at time point 1, time point 2, time point 3. This has a temporal sort of, in a sense, this is a recurrent model now, a model which takes temporal data.
Do you mean that the output of this network is learning the weights or the context relative to other words?
That's correct. To some extent, it's much more complex than this. I'll add the complexity one at a time. But to start with, you're giving your inputs, and then your inputs go through a fully connected neural network. This is just fully connected neural network, and you have the weights of omega. Interestingly, for now, these weights will be similar for all the words, all the inputs, all the X's, and it generates exactly the same output. You can imagine even you can make the dimensions exactly the same, right?
You say you're doing this in a window, so wouldn't your inputs be different? Like if you're looking at your neighbors, then wouldn't you have different numbers of neighbors every time you slide that over?
I'll get to that. That's correct. In natural language processing, for example, in natural languages, your sentences don't have exactly the same length. What you do, I'll explain it later how exactly the large language models work. You create a fixed length. You say, for example, my length is 1024, and then if your sentence is shorter, you just pad it. But when you create fixed sets. But interestingly, at each point of time, and you can create sliding windows depending on how you are architecting your model. When in standard form, each of these are like different words in a sentence, and you can have the full words depending on how many you're adding it. And I'll give some practical examples how, for example, BERT model, the first generations of like great-grandfather of ChatGPT, how they started creating like what assumptions they made and how they created the weights. But imagine in a sentence, each of them are words. In the genomic sequences, each of them are just one sequence. You're giving it one after the other. In behavioral data, each of them are one time point, depending on how you formulate your data. Is that clear?
So one quick way. Is X1 a single word embedding, or is that?
It's single word embedding. X1 is single word embedding. And I'll get to the embedding at some point when I progress. For now, imagine each word is represented as a vector. How we represent a word as a vector, I'll explain it. And in some, if you work with images, if you work with behavioral data type of things we collect, you have the luxury of your data already comes in a vector. If you work in natural language, or if you're taking genomic sequences, your data is not actually a vector. You do some embedding, and I'll talk about the embedding. And embedding is an important part of all this large language models. When I say language, from now on, I refer them to large language models, but it's clear they are not only applied to languages. But when you take the data, you take your inputs, you take a sequence of inputs, and then you create your values. Up to here, you have just your omegas and betas. You have your biases and weights, and this is, imagine, a fully connected network. And fully what it does, in reality, what it does, looks at in each of the embedding you have, if this was the word embedding, if this was different sensors you were monitoring at any time point, if it was like in a sequence, each of the genomic representations within a sequence, they look at within that word, how they are correlated. Within that word, how this embedding is correlated. For now, again, I'll carry on my examples with language, but you can imagine you can transfer it to any part of the work. If you're taking an image, will be within the mosaic of image you have taken, how those pixels are correlated. Here, you're just learning those weights. How you will learn it for now, you will start as any neural network, you will start at some point like a initialization with random weights, and then you will learn it. For now, let's assume we have the learning process in place. Let's just create the forward process and we come to backward. Then we create the values. And what we do then when we create the values, then each of these words, they will pay attention to to each other. Like from, for example, to X1, if we have three words, X2 and X3 and X1 itself, they pay attention. And then we have a weight of attention. For example, in a sentence, the words coming in that sentence, how much attention they pay to that, we learn a weight. Interestingly, from the embedding you take from that word, all the attention weights from one word to other, from each of the embeddings are exactly the same. Means X3 pays an attention with 0.6 to X1. And if you are representing your X3 with four-dimensional vector, every single dimension pays exactly uses the same weight. Is that clear? It's just to make it computationally tractable and computationally manageable. Does that make sense? If you haven't worked with neural networks, so I'm afraid this could come across a little complicated. But if you're familiar with neural networks, basically we have created a neural networks. Imagine these are three fully connected network, and the output dimension of input and outputs are exactly the same. And what we do from the output of them, we are drawing again just a direct connection, fully connected network to another layer with exactly the same dimension. And what we do here, from each of these single networks, we are adding a link to the every single other network with exactly the same weight. And that's basically they are the self-attention weights. For now, imagine we will learn the self-attention weights somehow magically, but imagine we have the weights here. It's just shown three of them. This is the attention that all the X1, X1, X2, X3, they pay to X1. These are the weights paid to X2, and these are the weights paid to X3. And imagine colors
Sorry,
here.
Payam, can I ask a clarification? How do you
Sure.
define these weights, these brown weights, 0.1, 0.3, 0.6?
You start with some random weights, and I'll get to the training how you define the weights. For now, assume we have a magical wand. We will define this weights. I'll come back to it. The training process. In the forward process, I'll explain the forward, and when we get to the end, I will say how in deep neural networks, what we do, we have a forward process. We get to a result, we calculate our error, and then we'll use our error to train the network. I haven't still got to the error. When I get to the how we calculate the error, I'll show the loop how we will start updating the weights. Basically, imagine this will repeat millions of times, and over a million of times of iterations, you gradually will start updating and finding what's the most optimum weight for this. Does that make sense, Fatima?
Yes, absolutely.
Well, you're polite. It doesn't make much sense. But when I get to the end of the process, you will see how we're going to calculate it. For now, let's assume we have the weights. Yeah, just take it from me, and I'll show you how we calculate it. Promise. For now, but when we are applying it, again, this is just the writing in a mathematical form I said. We have this omegas as values. We apply the weights to the values. We get the values. And then the attention weights, as I said, from each of these values is exactly carries the same weight to the next one. In reality, what we do, we are creating here a fully connected network. And each of these are fully connected network, and a fully connected network in this layer. The weights for the fully connected network on this part are exactly the same. This is a bit odd because when we created neural networks, you would have imagined each of these networks of this would have had different weights. Attention models, they share this weight, means what you're learning, how these embeddings are correlated to each other, they're sharing the same weights. It's a bit odd, but take it from me. And if you look at this, this is the weight you're learning for that, right? Does that make sense? Everybody looks a bit perplexed and puzzled. It's a very weird architecture in a sense, but it's a very interesting architecture as well at the same time. A lot of it's done also to make it computationally simple because they are sharing weights in large neural networks. And by the large, you will see as I progress, I start providing more tangible examples. You will see suddenly your dimension of parameters will go like in millions and billions of parameters. And you see how this sharing the parameters is going to help to reduce the computational part. But in the first instance, you have a word embedding. You have embedding of your data. It means your data, if the word was Paddington, will be represented by a vector. I'll talk about how you represent it by that vector. That vector has some values. That values will be here. And then these weights, we will learn those weights, and we'll create something called a value. That value now will be this Paddington again with the same dimension. These are the values after this network applied, right? Once we have created those values, then we learn how different words, now Paddington will have the same thing, train will have the same thing, representation, and we will learn what attention train provides to Paddington and Paddington provides the train. And these are the attention weights. Attention weight going from, this is like a 4-dimensional data. Going from this to this one, every single dimension will carry exactly the same weight. Like if the weight of Paddington to train is 0.1, means every single dimension will be multiplied by 0.1 of the train. Makes sense? You could make it probably much more complicated if you wanted to train different weights, but suddenly you can imagine your parameter space, we're going to go like mad, really. And that's how it's shown in a matrix world here. All the attention weights going from one word to the other are the same. This is writing it in mathematical form. One thing now attention model does, if by now you thought this looks odd and complex, it creates a little more complexity to it. It takes your input and creates something called query and key. These are copies of the same data. If you had your Paddington was represented with the 4-dimensional data, this was Paddington, and I explain how you create this word embeddings in a minute. But for now, take it if you could represent it with the 4-dimensional data, we'll create 2 4-dimensional data, 2 of the same network I showed, and we'll create exactly the same attentions for query and key separately. That goes to my earlier example to say information retrieval works based on a query and a key, and a combination of a query and key, you will find a value. In the self-attention, by basically creating layers in architecture, artificially we simulate this. At each point of time, we will take one word and we'll make it a query, and we will look for the keys, and then we'll find the values. When I show the architecture, you will see this. And then we'll apply a softmax, which we are getting closer of. If you're familiar with logistic regression and logistic models, if you have like a one-dimensional data, you apply a logistic function, you convert any data you have in any range between 0 and 1. Softmax is a similar model, a similar function which applies to multi-dimensional data. If you have an n-dimensional data, you can apply a softmax function. That was not doing justice to softmax, but you will get what I mean. You basically squash your data between 0 and 1. And in a lot of deep neural networks, softmax has used your final decision layer basically to create your output, and you will use that to calculate your error. Now, if we have started all this as random, my picture doesn't appear here, just forget about this. If we had started all these weights at random, we will create an output. And once we have an output in deep neural networks, you know, it's useful because we can now measure our error, and I'll get to the error, how we calculate the error, and we can start going back and training our network. But to start with, again, we have our values. These are like Paddington, train, I don't know, station. Each of them are multi-dimensional data. For simplification, it's not shown here. Like each of these x1, x2, x3, let's say this is x1, x2, x3 are multi-dimensional sort of data or word representations. Then we copy them. They are exact copies to start with. They are exact copies. They will go as queries, queues here, and keys here. They will just go to a separate network. And then what we do, we exactly learn the omegas for this, and imagine omegas as shared across all this, and omegas for this are shared across this network. And then we create the values of this. This would be the query values. This would be the key values shown here. I might choose other colors as well. Key values here. And then we learn here, we do a dot product. We just, each of this, you just apply the first one to the first one, you get this value. Just dot product of 2 vectors. If you had 2 vectors up by 4, if this was your query, if you want to do a dot product, just apply them. This would be your key. I just showed one transpose. You just multiply them, you get just one product, one value. And you put that value, that will become attention value. Yeah. For now, imagine everything has started random, and we are planning it. We haven't still trained it. We calculated. But Fatima's question was, how do you get the attention value? You just apply the queries and keys, and you get the value. That value to start with won't make much sense because it started with some random weights we have put here. But gradually we will learn it and make that attention more and more useful. Is that clear up to here? And you apply it, you will get it. And you run it through a softmax function. And once you apply a softmax, basically there will be between 0 and 1 over 0 and 1 or minus 1. You apply a softmax, I should know that. You apply a softmax function and you basically normalize it. And then what you do, once you have that, that will become your attention weights. These are the weights I was showing in the previous slides. Let me go this. These are the weights I was showing. These are the attention weights we are learning. So now we are calculating. For now, we haven't learned anything. We have just calculated the weight by sheer random, which is we've added some random information. But in reality, we have learned how each word gets sort of, each word puts some influence on the other word. You're just adding each word puts an influence on the other word, because each of this will come of combination of a query of, for example, x1 by key of x1 multiplication. Each word puts an attention to the other word. Is that clear? It's not very, but the more examples I provide probably will become more clear. In other words, we had our x-axis here again, and we apply the fully connected network that shows within each word, within each embedding, how different parts of our embedding gets correlated. And then from there, we calculated the sort of attention weights going for each of this from one word to the other. And then that becomes a dot product of them. We apply a softmax, and this will become attention weights.
What's the interpretation of the dot product in this case? Like, what is this? Like high level explanation for why you're doing that operation.
I show you. Paddington went to station. What you do in self-attention, at each point of time, you take one of this will becomes your focus, and the others will become basically part of the this becomes your query, the rest becomes the key, and you find how these contribute when you are interpreting the sentence. Now, there will be a cost function. We will train it based on something. For now, I haven't said that could be training based on, for example, you will mask a word and you'll try to predict that word, and you will try to find how your model predicts that well. But imagine we have a cost function. At each point of time, you are taking one of these values, you're taking one of this, the next point you are taking this. And at each point of time, you're saying how the others contribute when we are predicting a function to that word. For example, we want to see if this was a review, if this was a sentence, we wanted to see whether the sentence is a positive review or negative review, for example. I don't know what rate it was. Or in a lot of large language models, they mask a word and they try to predict that word. For example, you're masking this and you're giving this, you're trying to predict the other one. In the training process, you are calculating how the other words in the neighboring, how much they contributed to predict that word.
Is it indirectly, would it be completely wrong to say it's indirectly measuring similarity in the sense that the two vectors are pointing at similar?
Semantic similarity. You're looking at the semantic similarity towards what you're trying to predict. Yeah, not similarity of words, because Paddington has no similarity to station whatsoever. You are looking at the semantic similarity. Semantically, they seem to be more related. You are looking at semantically, for example, jam seems to be when it appears with any location information, has a negative intonation in it because it's referring to traffic jams. Right.
I was just going to ask the same thing, because if you were just doing this, it feels so. If it was just the word embedding, say the inputs, and you were doing a dot product, that feels quite like the cosine distance or whatever you use for word embedding. So, but then is it semantic similarity? Because you've already done a kind of mapping in your first layer from the word embedding to these other four outputs that may or may not, and obviously you're going to tune those. So I was a bit. That's why I just wanted to explain in English what's the difference between semantic similarity with just the level of two word embeddings. Cosine similarity, it feels like a dot product would give you something like that, versus what, because you're actually doing it on the output, the first layer. So I didn't quite understand how that.
Greg is much more articulate than what I said. Exactly. When you do the dot product, you're taking cosine similarity. I just dropped that information.
Yeah.
You're taking cosine similarity, and in a lot of information retrieval, classic natural language processing, you use to find semantic similarity. But my use of semantic similarity was not, strictly speaking, accurate. Here you are looking at how much other surrounding words helped you to predict that word or predict the meaning of that word or predicted what your cost function was. For example, usually the large language models are trained in two ways. The way you train it, first of all, you take an unsupervised task and literally you convert it to sort of a supervised task. By doing that, for example, what you do, you take lots of sentences, and each time you mask a word, and then you ask your model to predict that what word is going to be. You give this sentence, and millions of these sentences you mask it, and in that task, you are looking at how much the other words in surrounding contributed to predicting that word. Your model's output, let's say, if you're predicting words, your model's output will be a class with the size of, multi-class output with the size of your vocabulary. For example, in a lot of language processing, this size of your vocabulary is something around 30,000. Imagine in spoken English, you will have something around 30,000 sort of words you might want to predict. Take it in your world, see if you were trying to predict something, how many of the varieties you will have. And now in that 30,000 classes, for example, if you're predicting, what you're learning in a large number of iterations of sentences you have seen, how much the surrounding words contributed to predict that word. And that is the attention, how much attention they paid. The next time when you see station and you see a bear, you see station and bear, they will, over time, they will have higher attentions to Paddington. It means whenever you will see station and bear, if there's a mask works, you most probably will predict Paddington. That's exactly how ChatGPT works. Now I'll get to that, how ChatGPT needs to start from somewhere. But imagine by sequence of words, by seeing how sequence of words are, and by learning the self-attentions through a large training, has learned how the different words, they pay attention to the next one and start predicting what is the most likely one coming out. Interestingly, our brain does this completely now automated unconscious process in spoken language, right? And that's exactly how machines are trying to do that. And that's why there's a lot of argument now. I'll get more into this. We are creating machines which can think like human and can be more intelligent and more intelligent than human. Well, I'll get to that in a minute.
And differentiate between if the one word can mean different things, but if two words can mean the same thing, how does this work?
If two words mean the same thing, again, what you're trying to do is that happens. Like, imagine again, I'll use ChatGPT's example. If you say refresh will give you a different series of the same, you ask a question and say refresh will give you a different sequence of that words. Well, we'll find the different sequences. These are probabilistic models, sort of, to some extent. Part of it is engineering, how you do it, but at the end of the day, they predict probability of what is going to be next, or predicting what is going to mean. And then you will get in the sort of a series of probabilistic, let's say if you're predicting the next word or predicting what will be in place of Paddington, you'll get a series of probabilities. And the two words are different, but they mean the same thing. We'll have probably, if you learn it well, we'll have higher probability. Now, it depends on how many times you have seen one, might get higher probability, depending on what data you have given to your model. And in a lot of large language models like ChatGPT, what it does actually to prevent itself to get stuck, we'll do a random choice. I'll talk about this because in a lot of things, if don't imagine, the probabilities are not 0.9, 0.95, but 9.5. The probabilities are 0.0001, 0.0012. And when probabilities become very small, the large language models, they run a risk. They will pick very small probabilities and will go through a sequence and they will end up in a dead end. And one of the engineering methods is they will get the top 5 and randomly choose one and they move to the next randomly. There's a lot of information engineering goes into this. Is part of it is the model, part of it is how you design the model. But what you're saying is absolutely right.
If you change the architecture so that the weights in X1, so each one of these elements it's embedding, were not just shared from the values to the output, so you're actually learning those separately, then would you no longer just be learning semantic similarity? Because now, for example, like the structure within each word phonetically would now contribute to the attention that you would pay to neighboring words.
Probably you would create much more sophisticated model. I don't know whether that sophistication I would try to see whether it will increase, but what I know quickly you can become computationally intractable. Like already this models, but then I talk now how many parameters they need to do like a sort of like BERT, which is a very relatively simple compared to like GPT type of models. BERT is very, very simple. You will see there are millions and millions of parameters. But in reality, depending on what embedding you're using, if you don't share the question is for our colleagues online, the question is if the weights I'm showing here in green, if they are different, they are not shared across. If you learn different, for each word, you learn a different weights. And imagine in a vocabulary, you will have lots of words, lots of embeddings, and that to some extent could improve. I don't know what could also create more confusion to model because next time there will be different words here appearing and not sharing that word. Basically, you're learning different embeddings depending on where they appeared in your.
But how would that allow chat to make like a poem up? Like you need to know something about the rhyming structure or like the substructure of each word. So if that's not encoded in the network.
That will depend on how you embed the words. Word embedding is separate to this. Like the question is, yeah, how do you know this embedding is the best embedding, and how do you know that embedding is external to the attention model? Attention model assumes you have your embedding, and I'll have a few slides to show how you do embedding. In natural language, you need to find a way to do embedding. As I said, depending on some type of data, for example, what we collect from in-home monitoring data comes already with embedded data. It already has the embedding is already sort of represented. If you use genomic data, you need to decide how you embed data. I agree, but for attention model, that's external to model. Model assumes you have done your embedding. What it does, looks within your embedding, how different dimensions in your embedding contributes to attention itself. It's a little refinement of, because embedding is done with discarding any attention or anything. Here, you're refining your embeddings by basically teaching them to also to pay attention to the other words, because embeddings are usually they are not based on an attention model. Any other questions? You don't have to necessarily do that, but at some point you need to decide, like at the keys and queries, they need to have the same value, the same dimension, because you're going to multiply them.
We could have four range words, but then when they connect it to the next layer, which is a valid layer, we can shrink that.
Yeah,
Like
principally I use.
Had to be.
When I show the full architecture, now you will see this is still the first part of the attention model. When I show the full architecture, you will see how different layers, and you can see where you can change it and where you cannot change it. Because at some point, some of them, they need to be the same dimension of your data. Some of them, they don't need to be the same dimension of your data. But for now, seeing your queries and keys at the moment, they need to be the same dimension. And if you change the dimension, there will be some other implications I'll show in a second. But it's a very good question. Okay, the self-attention, the weights depends on a measure of similarity. Similarity. Now you take it, Greg is right. I emphasizing this is semantic similarity, maybe is not the correct one. Semantic similarity might say part of the dot product is the cosine similarity, but at each point, again, you're just creating a self-attention. You're basically creating artificially, you're creating a supervised, let's say, task. Each time you're putting one word at the focus of your point, and you're trying to look at how much similarity to other words they're providing to that. And there is no activation function, by the way. This is very, very interesting. Again, if for those of you who have designed neural networks, this might come very sort of counterintuitive. Up to here, in any of the networks I showed, I should have clarified it. There is no activation function whatsoever. This is like one of the interesting architectures. Up to this point, there is no activation function. Just directly apply the weights and just carry on, except you have here a softmax function, but that's not an activation. Then, but one thing I need to, again, to correct it, when I say fully connected perceptual models, I forgot to say they are not actually, they don't have activation function. And by doing that, you might just say, oh, wait a minute, the whole thing is a linear process. Because if you don't have any activation function, in reality, up to this point, again, I need to go back, up to this point, everything actually is a linear combination of just a bunch of weights. Up to here, they're just a bunch of linear regressions or linear combinations. Here you apply a softmax and normalize it, but the self-attention process itself is a non-linear process. And the more I talk about the architecture, you'll see why. Oh, activation function. If you have a neural network, let's say with 3 inputs, and imagine I just created one layer output. This is your W1, W2, W3, X1, X2, X3. Your neural network's output will be X1, W1 plus X2, W2, X3, W3. This will be the output of your function. Let's say it will be an O. An activation function, you apply this O to f of x will become f of O. For example, one activation function is called ReLU. ReLU function is 0. Let me just show it a different color. ReLU is 0 for any values, negative values. For any positive values, just outputs itself. That's like called this is one of the most common activation functions used at the moment in deep neural network called ReLU. Let's say if our value was 5, FAO will input 5. If our value was minus 0.1, output 0. And that's adds non-linearity in neural networks. Interestingly, there are different functions. There are like different functions. For example, they will have an output like this. They will have, I don't know, there are various forms of this activation functions. In a lot of deep neural networks, ReLU at the moment is mostly most popular one, probably. There are different variations of ReLU itself as well. Like there's a leaky ReLU, which will have negative, but very small sort of, what to call it, multiplied by coefficient or things. And I'm sorry if I'm not explaining the neural network concepts, because this is a continuation of the previous lectures I gave. And there we had a long, but if you're looking for background information, I think our lecture 6 last round, which is on the GitHub page, has a sort of a detailed descriptions of all the neural network functions. To continue, then up to here, our network doesn't have any activation function whatsoever. This is the matrix form of it. Now, each of your inputs becomes one of these vectors. Like if you had 5 inputs, this will be first one, second one, third, fourth, 5. I just squash them all as squashed in just in a vector form. Then you create now 3 copies. Up to here, I said you're creating 1 copy. This is a very, very interesting architecture. The first copy will become the query. The second copy becomes the key. The third copy becomes the value. The first 2 copies are used for one purpose, to create the self-attention weights. Once you have the self-attention weights, then you take this input and you apply the self-attention weights. Now you know each of the words, how much this one pays attention to this one, for example, because you have the weights here, you have calculated it. And then you create something which is called the output. And then when you've created that output, you apply a softmax functions for it.
Why does it need to be debugged? Because each dimension in your embedding is exactly the same, so why is the output just an n by n square measure? So it's capturing the weights between each word and every other word in the output, right?
Yeah.
But the dimensions you're saying is exactly the same for each dimension for each of the embedding. So why isn't it just an n by n output?
Is n by n?
It's d by n.
Oh. That's the self-attention.
Oh, okay.
This is n by n.
Okay, sorry.
And that answers, Olivia, your question, because you want this to become n by n, because you want to create sort of attention from each to the other. If this dimension is different by n, then you won't have for n inputs you won't have. You have to make sure this just follows the dimension of n, how many you have in your sequence.
So why are you combining the attention part with the values? I didn't understand this last step.
What you do, the question is for our colleagues again online, the question is why you are multiplying the self-attention base with the value, the input itself. I'll just go back a few slides. This was the very first one, which we had here. And Fatima asked the question to say, how do you calculate this attention weights? Basically, use the top part of that diagram. Where are we? These are the calculation of those weights. These are basically here, you're calculating the self-attention from each word to the other word.
Yeah, so the self-attention is telling you the amount, I guess, like the contribution of each words in predicting, for example, every other word. But then what's the interpretation of the output? And yeah.
Which it is, and
So-
but when you multiply this by that, then what happens is you have now told each input how much. Based on that, you have updated the weights of that based on how much influence the other words they had, because you're not taking every single of them. You're taking every single of them, not just one of them. And what happens is you're updating your values based on now attentions. Imagine if you had an embedding for your values, which you're just taking embedding. Now you're updating your embeddings based on the attentions, other words they provided. You're changing the values for embedding based on attentions the other provided. That's sort of the mathematical way of presenting. I had a sentence, and each of the words, they had an influence, they had a weight, and they came and updated my word embedding. Does it make sense? Would you like to have a break? Or shall I carry on? I booked this route till 12:30. Should I carry on? Another half an hour. It's good. More questions? I like this. I appreciate it. I think part of it is how I explain it. Part of it is also the the first time I read this, I had to read it 3 times. I actually didn't. I had to constantly go back and so wait a minute. How this works? And one thing I should have said to start: if you leave this room and you think I only understood 10% of it, you are far better than me, because the first time I read it, actually, I understood nothing. And I had to go and read it again, because some of it is not intuitively the way a lot of neural networks are designed. And I had to really pay attention when I was reading and looking at every of these figures. Oh, wait a minute, how they did this. And overall, it's interesting how they came up with this architecture and how this architecture works. But it's a very, it's something I don't know how this occurs to somebody to do this, but in a beautiful way, you will see this all comes together in very, very nicely, and suddenly has changed the entire sort of AI world. It's just this concept of how you create self-attention. But a lot of it is just like, if you look at the entire GPT and everything else, it's just this one diagram with much larger scale, which I talk about this. And I think up to here, if there are more questions, if you think I need to clarify anything, just please feel free to ask. I like to, because it helps me to understand better myself. Yes.
So in this first step, where you copy the embeddings just over to your values and keys and your so how do you end up learning different weights and biases when, like, I didn't.
Oh, we haven't learned anything yet. Yes, you're right. The question is, yeah, but all this started with sort of the random initialization for the weights. How are you going to update the weights? We'll get to that in a second. So far, it's just a forward process. A learning process will be based on gradients. Now we need to find the loss function to calculate the gradients. If I have the loss function, going backwards in a neural network is relatively something we've done for decades. Like you just, if I knew what the gradients are, but at the moment I'm not measuring against anything. At the moment I'm just putting each word as the focus word, and I'm learning attentions and I'm applying attention weights. But we'll get to that. You're right. Up to this point, model doesn't do anything. It just does a bit of more complex embedding. And a few things still we haven't done. I'll add complexity one at a time. At the moment, the sequences of these words still has no, like I could organize them in any different sequence and give it to the model. The model has not still looked at the temporal relation. There is a trick also to add the temporal relation, because in a sequence, in a genomic sequence, order of sequence is important. In temporal data, if you give from activity data, order of X1, X2 is important. If you're giving a natural language text, the order of text is important. So far, I've ignored a few things. I've ignored how we're going to update the weights. I've ignored the temporal dimensions. I'll add one at a time to this architecture. Apart from that, is that clear? In a very simple form, you take 3 copies of your input, use 2 copies, artificially make one of them query, one of them as a key, and you're trying to learn the self-attentions, how they pay attention to each other, and you calculate weights, and then you use the 3rd copies and you apply that, and you basically update your embeddings. With the caveat of our embedding still doesn't have temporal relation.
The other words, but then I don't see what's the point of value and finding with the attention.
It's a good question. For again, our colleagues online, the question is, what is the point of having this value when you have the keys and queries? How they actually did applying this affects the sort of paying self-attention. Imagine what I'm drawing here. I have two inputs and they are represented in 3 dimensions. The first thing we do, we learn a neural network. I'm not going to show all the network. Imagine we are learning a neural network here with no activation, which represents this. This is the inter-word sort of embedding relationships we are learning. And the weight we are learning this is shared across all these words. And then we have these values here. And what we are doing, these values are linked to 2 other exactly the same dimension values. Which what we want to do, we want to learn self-attention. Like this is for word 1, word 2. We want to learn how much this word pays attention. Oh, I haven't drawn anything. We want to show how this word, which we have learned from here, how much attention it pays to this word. From each dimension of it, we draw a line and we pay the self-attention. Up to here, this is this part of it, the architecture, which learns the self-attention weights. Once we learn the self-attention weights, we haven't done anything to the input yet. We have just learned attention of x1 to x2. Now, what we need to do, we need to create again the same input, again with a fully connected network. What we do, we create another version of this, which will have x1 and x2. And then what we do, in that one, we apply the self-attention weights to that.
Training set of value.
These 2 inputs, the green box, after we have created the self-attention weights, we don't need them anymore. They're out of the architecture for now. Obviously, we need to learn the weights and things, but for now, they're out of the architecture. The output of them are just the self-attention weights. What we use the queries and keys to learn self-attention weights. Once we learn the self-attention weights, we don't need them anymore. For time being, of course, we need to come back and update them. We don't need them. We just need the self-attention weights to go back to this values we had to apply the self-attentions.
Because, for example, even though with the self-attention network itself, it can already have like really powerful in terms of predicting the semantic similarities between different words. But then
There's no self-attention. This value has no self-attention. Attention weights come from here.
yeah, I mean, like from the top part, it can learn, the purpose of the top part is to learn the attention between different words. And then, but we can't stop there because this gives us no comparison to learn the loss function. And therefore we want to apply this attention to the actual values and then give an output. And then so that we can compare whether that actual like is predicted correctly or not. And
That's
then
correct.
update.
That's correct. Yeah. That's correct. The self-attentions, they just give us the weights. They don't do anything. They just give us the weights, how each word pays attention to the other word. Once we take it, we want to just apply it to our inputs and then take it and apply it to softmax. Yeah. More questions?
Yeah, just a question about notation. So I noticed next to the biases, you have a 1. Is that literally just a vector of 1? So is that what you're initializing it?
But biases are identical matrix. Let's call it isomorphic. Because I'm showing it matrix, they are just values are here. You just
Oh, that's how so you write that as 1 transpose, is that what that means? Yeah, no.
yeah. This
Okay.
is identity matrix. This is identity matrix. Yeah, this is the identity matrix. Beta I basically have an identity matrix around a sort of the instead of i's, the ones you will have the betas. An identity matrix. Then you write a matrix form. You just want everything to be multiplied by matrix. You make that as a matrix form. If you multiply it, you'll be just multiplying beta to each of those weights, adding so beta. It's not an addition. Right. Should I move? Again, if you're finding it confusing, don't worry. You are not alone. I found it confusing the first time I read it, and it's still occasionally I confuse myself. Then to sum it up, what we did, this part, only learn this, nothing else. Only learn this attention of xm to xn. And that helps us to move from this point to this point in our architecture. The rest is just here. The important part actually is here, because that's the input. Make sense? Then we create 3 copies of the input. One copy we will use it to calculate the final for now. It's not really final. And the 2 of the copies, we just use it to create the self-attentions. And so far up to here, after an hour, still I haven't told you how to update the weights. I will get to there. Just bear with me. And it's still everything. It seems to be we take random and go, but a lot of it interestingly works with the neural network. Then showing it again in a different word, you have the words now. You have sort of embeddings. Imagine here we have thinking machines, and we apply an embedding. I'll give some examples, and I'll tell you how in natural language processing you create embedding. And then here you create, here now you see the dimensions a bit different from 4-dimensional inputs to 3-dimension. You create queries and keys and values, and each of them will become a matrix, and then you use the matrix, sort of showing the matrix multiplication for. We create first embedding, then create queries, keys, and values. We apply queries and keys. We get the self-attention between the 2 words, and then we use that self-attention to calculate how different words are getting correlated to each other. Make sense? There are a little more complexities when you're creating. You also normalize the values. The problem is, if you keep applying this, adding these numbers, you multiply, do dot product of keys and queries, depending on your embedding. Suddenly you might start creating very large numbers. And the problem with a lot of neural networks, if you work with neural networks, if trained it, we don't like large numbers, because when they become very large, they can dominate suddenly, and sort of that domination can create a sort of vanishing or exploding gradients for us, because whenever we calculate the gradient, suddenly if number suddenly becomes very large, might create a very large gradient. Basically, take it from me, we don't like large numbers in neural networks. What we do always, we try to squash them, and here we divide them. Don't ask me, I don't know where it came from, by square root of the dimension of your embedding. Dimension of the query you had, you multiply, you divide it by that to basically take the number down, to squash it. The designers of the attention model, they suggest that you divide by the square root of the dimension, not the dimension itself. Basically, that brings the numbers. For example, here, if the numbers were 112, not 96, brings them to much smaller. And you can see when you make them smaller, that now the sort of spectrum of the change, the numbers are closer to each other rather than having 1,000 sort of units difference. And when you apply softmax, they become a bit closer. And once you have created softmax, basically you have squashed them out to normalize a value, and those will become your outputs. Outputs for now, and then we'll go to across the model. Any questions so far? Just in a vector form. I mean, if you are not interested, but just showing the same thing. If you had 2 inputs, you just stack them up and becomes a vector. You multiply it by weights of your query, weights of your key, weights of your query, weights of your key, weights of your values, and you get the query key values, and the multiplication of this 2, dot product of this 2 will give you the self-attention weights. And you will use the self-attention weights to multiply it by that to calculate the output, and this will give you the Z. Imagine now you have created a self-attention, which just only thing it learned how each, if you had taken each of these words, how much other words contributed to that in terms of being relevant, like, and you will do this based on functions that, imagine if you were predicting Paddington, how much each of these words would have contributed to predict the word there should be Paddington. Take it like that. Imagine each time if you mask one word in the sentence, put that as your attention, and you're trying to see how much other words would have helped to predict that word should be Paddington. Probably if you look at the entire Paddington series and learned all the internet, Wikipedia, everything, you will say probably jam has the highest, should have the self-attention weights here, because you will see jam, it seems to be always having higher weight. Does that make sense? And probably in the longer sentences will be more words contributing, and previous sentences to contribute to the next sentence. But you're getting to sort of a probabilistic model. The self-attention in principle, at each point of time, we'll put one of the words as your attention, and we'll look at how much the others they're contributing to predict that word. For now, if you're masking it. And up to now, our network predicts our attention embeddings. Hasn't done anything yet, hasn't learned anything so far, hasn't updated the weights, just has calculated the disease for us, which are the attention embeddings. Once we have the attention embeddings, one thing self-attention does is, going back to my first, when I showed the picture of Paddington's adventures, and I said, pay attention to the umbrella, to the bear, to the text, and suddenly, did you pay attention to the chimney? Interestingly, when you create a model to pay attention, if you just create one sort of attention model, your model might just learn to pay attention to certain things, not be enough to have multiple attentions to multiple details. The self-attention architecture is sort of created a multi-head beast. Basically, what it does, it creates the same design, this part, the whole thing is sort of multiplied, is multiple times copied and created multiple heads. In parallel, you're going to learn multi-head attentions. In reality, you're learning exactly the same things, cues, keys, queries, and values, but you're learning them multiple times in parallel. The assumption is, heuristically, each of them will end up paying more attention to something. And heuristically, if I multiply them multiple times and I create multiple attentions, each of them, they will learn, they will all start from a random point, and they will start paying attention, and I will train them to pay attention to certain details, and over time, some of them will become more sensitive. Take the, you are the neuroscientist, takes the human eye, part of the sensory visual cortex will pay attention to the edges. Part of them will pay attention to color. Part of them will pay attention, I don't know, to changing details, right? And each time they switch on and off between themselves to send information to the brain. Human eye has learned that by biologic evolution, or whatever you consider for that. In this case, you're telling basically your model with multi-head to learn to, basically you create that evolutionary process. You let the model with multiple heads start learning to pay attention to different details. Does that make sense? And the more heads you have, probably the better. The problem is each head you're adding, you're creating a lot of computational complexity to this. And a lot of these large language models, they need huge amount of computation to do the process. It again becomes a choice of how many heads you're adding. But in reality, when the attention paper came out, a part of it was multi-head attention. Multi-head attention is just the same attention, now multiply it many times. If by now you found this architecture confusing, probably this confuses you more. But some of the original models, they had up to 7, 8 like attention heads. And I'll talk about like GPT model, and I'll tell you like how many attention heads GPT has. Make sense? It's the same architecture. Now I have multiplied it, not multiplied it, multiple copies you have created, and you're calling it multi-head attention.
Is 7 like arbitrary?
Yeah, I think the designers started creating, I can't remember, the first model I think had 7, if I'm not mistaken. It's an arbitrary number you create, and it probably depends on computational and complexity.
It's just because it works.
Because it works, exactly, because it works. My feeling is, again, like anything else, at some point you add more heads, probably will become better and better, and there will be a breaking point, will create more confusion. But I haven't seen, at least I'm not aware of somebody looked at what would be the optimum head. But I'm assuming. But massive computational complexity, like look at the number of parameters, number of keys and queries. And so far, we haven't even trained it. If you have trained a neural network and calculating the gradients and updating it, and you might just get to a point, if you create a lot of these variations, you get to a point you cannot actually create a network which converges. Because in neural network, you want to minimize your error, and you might just create your architecture so complex and requires so much data and so much computational power and so much precision, you may never create a model which can opt. There will be an optimal space, but this optimal space in a space of 1 billion parameters. And combination of 1 billion parameters will give you a massive decision space. Where you find it is a computational problem. It's not, in theory, more heads probably should make it better, but the more heads you add, you're adding more parameters. Let's say if you have 1 billion parameters, combination of this 1 billion parameters will give you somewhere, a combination of this will have the best decision point. The problem is we don't have really mathematical ways of calculating that. And a lot of things we do in neural networks, they're heuristic. We'll just look for the space usually based on gradients, based on the error and rate of error. And finding that space might not become computationally what computer scientists say tractable, becomes intractable. Again, to make it simplified, if you have multiple heads, what the designers of attention model they did, they said if you had multiple heads, just concatenate them put them on top of each other. Just don't make it more complex than what it is. Just if you had 7 heads and each of them they generated like a Z, just put them on top of each other. Now suddenly each of the heads will create sort of an output. You just put them together, concatenate them. This makes sense. At least for this part is an easy solution. Okay. All in one. By the way, this is Jay Alamar has a very interesting tutorial on this. I looked at it and it's very visual. I've taken some of the those I've referenced it from his tutorial. Is again, if you want a better explanation, you can look at that as well. Is good. Now take the 2-word embedding here, X. We will have multiple heads, and for each of the heads, we will have queries, keys, and values. And then we calculate those attentions based on them, and the attentions will create Z0, Z1, Z2, Z7. And what we do, we just put them on top of each other, concatenate them, and then we apply. We take it to the rest of the process. This is the attention weights, and then we create the final Z vector. These are now coming attentions from multiple heads as well. While the whole thing was heuristic, you created multiple versions of that heuristics to now learn different different attentions from different starting points. Yes.
So, like, why are you splitting across the K heads? You just initialize these just randomly, and then you like essentially just.
Why you're creating multiple parallel ones?
Yeah.
Because wherever you start randomly, and when you train it, your attentions will converge to a certain weight, right? At some point, you will converge to a certain weight. You are creating a parallel wall to that. You're creating parallel attentions as well. Because your model heuristically is going to learn, you're letting the model to learn in multiple attention spaces for it.
But there's nothing sort of structurally that sort of steers each head of the 8 in kind of different directions. You don't wonder why they don't just all converge on the same thing and become kind of redundant.
But that's a good point. I've been seeing that. My understanding is because they start from random weights and they become random states. Probably heuristically, they will add up a random. You're initializing your model to look at the attention space from multiple random points, and each of them will end up in an optimum point. But heuristically, it's less likely the optimal point to be the same.
And then you just average them.
You put them together, don't average them. You concatenate them, then you create sort of a new embedding which has all the attentions on top of each other, and you use that.
What's the W0, W norm, the cost?
These are the attention weights applied to each of them. Oh, so sorry, there's a fully connected network here. Sorry, my apologies. There's a fully connected network.
But
Check
you
it.
just, okay, so you just concatenated the outputs of each of these heads.
And then multiply it by, then feed it to a fully connected network again.
Okay, wait, so the columns are now the input words weighted by the self-attention network.
Yeah.
Across all of the heads. Just
Yeah, it's it. Yeah.
And then,
You multiply it by, you add it to another fully connected network. There's another network on top. I'll show the architecture.
oh, okay, now there's another network coming.
There is another network.
Okay.
This is another network. This is another network. You add it to another network. The intuition behind it is, as I said, if we create attention, we will start from a random state, and our model will learn the attention weights based on a gradient function, based on a loss function. But our starting point will have an effect of how we start, because we start random. At some point, we find an optimal. And that optimal point will be sort of influenced by our random state. If we create multiple heads, we're basically allowing the model to look at the multiple spaces looking at this attention weights.
So at the end of this next network, what is the output trying to predict? Like, what are we going to be minimizing? At the end?
So far, nothing. Just bear with me. We will get to that. For now, we're just creating our embedding. We are just carrying on with our embedding. So far, we are not predicting anything. So far, we are just embedding our attention. Now, rather than having one attention, we have created 7 different attentions. Like I ask you to learn your attention. You learn a different attention. I learn a different attention. She learned a different attention. And we put all our attentions together and we created sort of a matrix of multiple head attentions. And then we feed it to a deep neural network. And that neural network will learn, probably towards our cost function, will learn which attention works better. Right? Because we are feeding it to fully connected neural network, because from here, your inputs goes to fully connected network. If you train this network well, we'll learn which of the features have better predictive value.
Yeah, but it's because you're going to do backprop, so you can't do
Yeah.
backprop unless these are all concatenated. That's
Yeah.
what you do.
Yeah. Oh, yeah.
Yeah.
The whole thing works based on backpropagation and gradients. The problem is I cannot tell you how you calculate the gradients until I provide the full architecture. But imagine if our architecture stopped here. If our architecture stopped here, let's say you would have predicted in my empty space, the word would have been Paddington, would have been bear, would have been water, would have been X. And then you would have said, if the model predicted Paddington with error of 0.1, you will use the gradient of that, you feed it back to your model and start updating all the weights. Make sense? But the model doesn't stop there. But imagine if you just stop the model there, you would use that, you put a sort of a logistic softmax there in the end, and you would have said, now look at what you predicted. And based on that prediction, you would have calculated the errors. Yeah. But model doesn't stop there. If you think this is complex, bear with me. You will see more complexity. This is the simple part. Okay, should I carry on?
I was just going to say, it feels like you could have, it'd be interesting to know what the effect of the different number of heads is, because it feels almost like you could have got to just as good a solution by just some different approach to the optimization to the gradient. So like, it feels like you're forcing it to optimize in a certain way by having 8 and saying, okay, one of the 8s, or maybe it needs all 8, I don't know, but in terms of the weights they end up with after the training, it feels like maybe that in a different architecture could effectively just produce the same thing, unless it needs 8.
I think they have different initial conditions. So what happens is that you're more likely to have one of these heads that will converge on the right solution. And so when you then do backprop, the likelihood of you finding one of these self-attention weights or whatever that's actually good and making a prediction is going to be higher.
Right.
Because otherwise you could just have you could just get stuck.
Yes, and it's just a bit rubbish.
Yeah, exactly. So I think the 8 is just arbitrary. It's just basically it works.
Greg's questions are always very clever. I'll get back to your question. No, it's actually there's some work. I'll get back. For our colleagues online, the question is, actually, you could have come up probably with more clever design. You didn't need all these multiple heads. You could have just optimized it with less parameters. In fact, the new developments in large language models, they're largely focusing on reducing parameters. So yesterday, I came across a work. They were saying we are getting similar performance with large language models with 1,000 times of less parameters. Now, a lot of work is focused, do we need all this complexity? But for now, what you do, you create 7, let's say, heads, and you don't know which head is actually working better. You're assuming because they all start at random and you're training with backpropagation, some of them might work better than the others. Then what you do, you put them on top of each other, you create a new vector, And the easiest way in deep neural networks to see whether something contributes better or not, feed them to another fully connected network and let the network decide which features contribute more. In reality, once you have trained it, this fully connected network, which is this part, I'm showing it with the red, what we'll do, decide with some of the Zs might get a very small weights, means you're just switching off those heads. Those heads don't contribute anything. And Greg's point was maybe there could have been a better architecture. You could have just calculated it along the way, or you just could have estimated it before even creating this multiple heads. I agree with that and a lot of it. But heuristically, interestingly, this worked really well. And the OpenAI and GPT and all of them, they used a very similar architecture with a lot of data engineering and things to use it. And it seems like it works really well, but doesn't stop here. Is the architecture is much more complex than this. How many of you have lost so far? Should I carry on? Okay, the next step is one thing we have two things I still haven't explained. Roughly, I explained how we're going to train the network. I will come back to the training after a few slides. But one thing so far I have largely ignored, and that has been the position of these things, because in a sentence, in a genomic sequence, in a behavioral temporal order, the order it matters. And here we are just saying, oh, you feed X1, X2, X3. But if you looked at our network architecture, if you change the places of all these inputs and outputs, that doesn't change anything in the architecture. Architecture could be this arbitrary, how I say you feed here. Let me show you, go back. If I'm saying feed X1, X2, X3, you might just say, well, what if I feed them in a different order? Your network will exactly learn the same thing because the weights are shared. Then how do you tell the network the position matters? Does that make sense? And that comes with something. I think the attention, people who wrote the attention paper came up with something really, really cool idea, and they call it positional encoding. Then if you have, and I haven't talked to embedded, there are lots of things I need to explain and refer it, I'll talk about it, but bear with me. Imagine if your word is represented by a vector. Let's say Paddington. Why are my examples? Paddington. I watched too much Paddington. Paddington went to the station. And imagine this word Paddington has become this embedding. Yeah, we somehow, I'll explain how we do the embedding in a minute. But we have created this embedding of 4-dimensional embedding. And now we want to tell our sentence, and Went has another embedding. Let me just show all of them. And I'm not going to use the auxiliary words. I'm just going to make the Paddington, Went, and station. Imagine each of them, they have an embedding. Like an embedding is for the words is the same dimension. All the words become a 4-dimensional vector. And there are methods to learn this. For now, bear with me and imagine we have a way of taking these words and converting them to vectors. What we want to do, we want to tell our model where the position of this is. What would be your first sort of intuition? How do we do this? 1, 2, 3, exactly. That's what I also thought. And I struggled a lot to at first to understand actually how the positional encoding works. I just said, okay, we give this one, we say is 1. Oh, sorry. Let's say not 0, 1. Computer science is always everything starts with 0, 1. What did I do? 1, this is 1, 2, 3. And what positional encoding does, how do we embed this information into this vector? Because we don't have any other dimension. We have to somehow add that to the, because our model doesn't get position separately, gets only these vectors. How do we add this to the vectors? Add to the bottom, then we are changing the dimension, and your model will assume that's a feature. Won't understand that's a number. That would create confusion. We don't want to do that.
Weights if they're connected together.
That's exactly the people who did the positional encoding they did. But what they did, let me just do this. Oh, I should have talked about, let's say if we had the words for now. If we had our words, if this was Paddington, this was Went, and this was a station. And imagine we had some numbers for this 0.1, 0.2, 3, 0.4, minus 0.5, 0.2, 3. Oh, sorry, one of them is more than the others. I can't even draw it something proper. Yeah. A word embedding will look something like this, right? And if we wanted to tell the order, we wanted the order of this to be 1. Order of this will be 2, and order of this will be 3. We need to somehow add this. One way of doing it is just add their order to the value of this. Just basically add the order to the value of this. Say this is positional encoding people, they took this approach. They said, add the value to this. Just update the weights, update the embedding by their position. Just the position, if it's 1, just add the 1 to the value. Just Dave started very simple, and you'll see it works. The problem was, how do you add that 1? Should you add 1, 2, 3, 4? The first thing is then the length of sentence will have an impact. If your sentence is long, then will have an impact. How do you do something relative? Another thing is, where do you add it? Here, my encoding has 4 dimensions. Where should I add that? How should I add that 1 to the 4 dimension? And any suggestions?
You could add it to all of them. You could add it to the nth element of it according to its word position.
There are different ways of doing it, and there is no correct or wrong way of doing it. One way of doing it, you might just say, well, I'll create a binary encoding, and 1 becomes 1, 0, 0. 2 becomes, and I create this. 2 becomes 1, 1. No, 1, 0, 0, 1, 0, 0. 3 becomes 1, 1, 0, 0. Does that make sense? And I'll add it. Binary encoding seems to be a nice arrangement. The problem with binary encoding is if your sentence is long and your embedding dimensions are small, you're quickly going to run out of space because there's a limit how you can do it. Then in reality, this is not going to work, right? You can change the different numerical systems. You can say, well, I can do base 16, base 18, or whatever, and then, well, I can fit more data. But again, by doing that, you're creating large numbers, you're adding it, and you're going to bias it. People who did positional encoding, they came with a very, very clever idea. They said, rather than doing this, came with something, which they call it, do a sign function. Rather than doing this, look at the sign of their position for now, and take the sign of position and add the sign of the position, and each based on each dimension. For example, is the position divided by dimension? I think is it? I can't remember, but take a combination of this. I'll show you the formula in a second. Say for each of this, say where the position was 1, and the first dimension will be 1 divided by 1. The first one will be 1 divided by 2. The third one 1 divided by 3. For each of the dimensions, create a sort of a sign value of it. In a sinusoidal.
So it's like you encode it around a circle, and then you take the position, the sign of the angle.
So it's and do this, and then for first position, you just take the position of the first one divided by each of this in the dimension you're referring to. The first one, for example, would be the sign of, let's say the position here is 1. The first one here for the first Paddington will become sign of 1 divided by 1. The second one will be sign of 1 divided by 2 because it's the second dimension. The third one will be sign of 1 divided by 3. This one was sign of 1 divided by 4. Move to the vent. This one would be sign of, now position is 2 divided by 1, and carry on. Does that make sense? Just take their position in the embedding and do that. That's a clever way of taking it. There is a problem here. And that problem is, if you take a sine wave, if you take a sine function, goes like this, right? And the position of 1 and probably for 6, if you calculate it here, will be the same point on the cycle because it goes as waves. And they will have a trick to compensate for that. I'll show in a second, but you will see. But for a second, bear with me. Does that make sense up to here? And they use that and they call it positional encoding. And what you do with positional encoding, once you have calculated the sign values, you just literally add them up together, add with the vector. Just a simple addition. And I looked around a lot in the internet to look at positional encoding. There's only just one somebody had really clearly explained it. There are lots of people say, oh, do positional encoding, but in reality, it's very, very simple to calculate this. Does it make sense? I think I've referenced it somewhere. Just somebody wrote a blog post, and obviously the people in the paper also explained it, but somebody took wrote a blog post about it and explained it really, really well. Now,
values just like tending towards smaller and smaller values. So
exactly.
then so longer sentences.
I'll show you in a second, and you will see how this is going to evolve. Yes, depending on your position. But basically, depending on which dimension each dimension in your embedding will have a different value. Does that make sense? Because what you're coding the position, and for each of the dimension, you're adding a value of that position.
But these values are like much larger for the words at the start of the sequence. So like position 1. And then
The sign of the sign value always will be with -1 and 1. Will never become a big number. Right? The sign, if you take the sign function, basically you're creating values between -1 and 1 to start with. And then looking at you by adding the dimensions to the formula, you're also saying which dimension of the embedding you are adding the sign, and you're equally adding it to our dimensions. I'll show examples of it and I'll explain it a little more. You seem still not convinced.
it just seems like later positions in the sequence are going to have smaller weights. Okay, anyway, yeah, that's not.
They will. I'll show you because you're going in a sign, depending on the first dimension of them might have a smaller number. In different dimensions you will have. Basically what you're creating sine waves with different frequencies, and then you're mapping them to different frequencies. At different frequencies, different positions will have different values, and different dimensions will have different values. That's, I think, what makes positional encoding very interesting. When I show some graphical.
I see how it's a science, because if you're dividing by 1/2, then 1/3, then 1/10, it's tending towards smaller and smaller values. So your sine is going towards sine of 0, which is 0. So it's not.
And then for the number 10, the first dimension will have a larger value because it will be 10 divided by 1. But as you go to the higher dimensions, the value will change. Because if this word is your word number 10, now the first dimension of it will be sine of 10 divided by 1. And then this will be 10 divided by 4, for example. The values are changing per dimension, basically. It's a good question. I struggled to be first time.
No, I was just going to write that script, and I think
I just did that. But I didn't appreciate you had different values per dimension. That makes sense.
Yeah. And now, one thing I haven't so far talked about it, I've assumed each of these words are represented by a vector. But I've never said where that vector comes from. I said in different domains, some of your data might come in a vector form. At least in natural language processing, it doesn't come in vector form. The traditional way of doing this is you create something, you call it AGO words, which was the title of my previous slide. What you do one-hot encoding. If you're familiar, you create a vector. The length of the vector is all the vocabularies you have in your language or whatever you're processing. Imagine if you're processing Wikipedia, every single occurring word will have a representation here. And then in each sentence, each word, you will just say if that word appears here, this will be 1, the rest will be 0. This is an. I don't know, the second one will be the second word, and so on. If you're familiar with one-hot encoding, I've talked before in the module about this, but have a quick look. It's a very simple concept. You will have a matrix which is a sparse, sparse, and only the value, basically you have, if you have 30,000 words in your vocabulary, you have a vector of 30,000 words, and only each time for a word, just one single of them will be on, the rest will be off. And that's called one-hot encoding. Traditionally, a lot of language processing, a lot of natural languages processing relied on one-hot encoding, and a lot of sentences and documents, they looked at the number of words appearing in document rather than just single word, looked at the entire document per document they created it. And there are some terminologies like term frequency, first term frequency, TF, IDF, if you're familiar, which normalizes this. But here our focus is on words, and we want to create an embedding which is not really sparse. This is sparse one-hot encodings are not very good for machine learning, a lot of neural networks, because they always have one value, the rest are zero, and that won't give us much value to create. We want to create something better for representation, and that's called word representations. Attention model is independent from that, assumes you have your word embeddings, but I thought it would be useful to tell actually some of them how they work. One of the ways of doing it, there are many ways of you can create it, but usually you start with one-hot encoding. And one of the ways of you create it is a model called Word2Vec. Interestingly, again, came from Google Research. And they create a neural network for this. What they do one-hot encoding, and then they create a word focus. And then they see how the other words, basically the context words, help to predict that word. And they create a neural network, which you are giving this one-hot encoded values, one-hot encoded values of this terminology. I'm just looking at if I have a graphical representation. Imagine these are one-hot encoded words in your sentence. You are giving them to a network, and then you are learning some weights, which basically will predict the missing words, for example. And by training that network, once you have created, this will become this purple part becomes your embedding. Basically, your model learns that embedding for that word. Interestingly, this uses itself a separate neural network. Now, a lot of word embeddings, they will use, this is just one way of doing it. For word2vector, this is called the model, and you can find the code. The code is relatively simple. You just create a network, you feed a lot of data to it, and you make the model to predict. And once you have converged to something, your model can predict the words correctly. And this is you have a multi-class, basically a classification problem, and the layer is the words you are trying to predict, the size of the words. If you have 30,000 words, that will be 30,000 words. And your model basically is a neural network, just learns to predict that. And once you have learned it, that will give you the representation. Just one way. There are existing codes, there are existing libraries. If you're using any Python codes, there are just the existing libraries. You give your text and will give you the word representation. Once you get your word representation, there are, again, different models. In this one, you're giving one-hot encoded inputs, and you make the model to predict. In a skipgram, what you do, you're giving a unique word, and you're letting the unique word to predict all the other words close to it. You're doing the other way around. In this version, you are giving one-hot encoded, and you are trying to predict the missing word, and you are training the model to predict the missing word. In a skipgram, you are giving the unique word, and you're training a model basically to create all the context words, the other way around. And you train your model. Once you learn it, this becomes your representation. Each of them will have a different ways of learning the representation. But in reality, what they do, they learn the semantic relationships, the semantic similarity between different words, or how the words can be embedded. Like, let's say if you do this, probably, I don't know, station and train will have similar embeddings logically if you train it, because they will always see train and station appear together, and they will have similar representation. Very 3 minutes sort of tutorial to word embedding and how you do in natural language processing. Once you have done that embedding, which is what you do, you create this embeddings, and then you have the positional encoding, and you just multiply them. Sorry, you add them, not multiply. This is a plus. You just literally add them, and this will become your input with positional encoding. With positional encoding. Does that make sense? That's how attention model gets sort of over the positional encoding problem. Basically, takes the data and does the positional encoding. And to be able to do that, takes the position of the input. That's where your position appears. For example, Paddington is 1, position is 1, vent is 2, station is 3. That's the position. Then I is the dimension, is the whole dimension that you have used for the size of embedding. For example, in our embedding here, the example is we have, I don't know, 5 dimensions. And I is this i's dimensions in the embedding, and calculates this. Let's say for the first word, for the Paddington, this will become sine of position is 1 divided by 10,000 times 2i divided by, here we have 5 dimensions, 5. And I will move for this one will become 1, for this one, 0, sorry, 0, 1, 2, and 3. You're creating sign representation. You can write here in 3 minutes, you can write a MATLAB code to generate that. Does that make sense? And as I said, if you take the position, position is fixed, and you change position is certain position is fixed for each word, and the I changes, and the D is always fixed because the word embedding, the embedding dimension is always fixed. But if you take the position for a second, position of like 0 and 6 here, for example, I think will create the same value. But if you change the I constantly, then in different dimensions, you're going to create a different set of representations. It means in some dimensions, they are similar. In other dimensions, they will be different. In reality, what you're creating different sine waves with different frequencies, and you're using this for your embedding. Does that make sense? Very clever way of creating a positional embedding. The simple way would have been our just binary representation. The only thing is we would have run out of space for our binary representation. That would have been very simple and a straightforward way of doing it, but we would have run out of space. And also would have been 0 and 1 is not ideal. You're just adding either 0 or 1. Here you're adding some fractional sorts of representations. The attention paper doesn't stop here. Add one other twist into this. Again, if you think the model is not complex enough, adds another twist into the positional encoding. But even an odd ones, they will use a sine or cosine embedding. Don't ask me why. Apparently, this gives you better representation. Then one of let me see. These ones, I think, will use the sine, if I'm not mistaken. And the even ones and odd ones will use the cosine or other way around.
I'm guessing a lot of this was found through trial and error.
Amazing. This is one thing I don't know why combination of sine and cosine. I understand that perfectly. I know the mathematical description of sine and cosine move exactly opposite each other, but how the combination of this, how they came up with the idea of using in even and odd, adding the sine embedding and cosine embedding will create a better representation in temporal. I don't know where they came up with the idea. That's the entire positional. Is that clear how positional encoding works? Because this was actually this was the part the first time I read the paper, I understood nothing. Interestingly, the other parts I slightly understood. This was the first actually part I had to go and reread it, but this seems to be the simplest part. And one thing was missing in a lot of descriptions. What do you do when you calculate this positional encodings? In reality, you just add it. Also goes back, I don't read carefully. You just add it. You don't do anything. You just add it to your word embedding. But you can come up with your own ideas how you do positional encoding. I'm not saying this. This is the best way of doing it. And if you have a very clear descriptions, put a blog online or post something, you will be very popular, because I find it's very little material on actually how you can do this. Okay. It's 12 o'clock. Shall I carry on? Okay. Then once you have done that, now imagine our input. One thing I had ignored so far, I hadn't told you how we do the positional how we do positions. Now our model has the embeddings, which are external to our model. They come with embeddings. We do the positional encoding, and we tell the position of the inputs. Now, no matter how, in what order you give the inputs, doesn't matter. They have the positions embedded into it. Right into them. In what order you feed it to the model doesn't matter once you have done the positional encoding. Once you have done the positional encoding, then we have these queries and keys, and we use queries and keys to find the attention model, and now how to find how each word pays attention to the other one. And when we use that to multiply it by the value, sometimes I show it on the screen. I forget people online won't see it. And we multiply it by the value itself, and also we do. Before I forget, we do also scaling here when we are calculating the dot weights to just stop if you've done trained neural networks, you know, again, large values, you could create vanishing or exploding gradients. Just to avoid that, we just scale it down by square root of the dimension itself, dimension of the Q itself, and then we get the self-attention. Now this is the result of the self-attention. So far, our model has done the self-attention. But the self-attention paper architecture didn't stop here. I said had multi-heads. Here I've shown two, not me, Simon Prince has shown 2 heads, but you have multiple heads. Some models might have like 7, I don't know, the different heads. And each of them will have their own self-attention weights. And what we do, we concatenate them together and then feed it to another fully connected network. Yeah, so far so good. If we have done it, then we can now, what we were predicting, we can feed it and start predicting. And that becomes our sort of transform layer, but the transformer architecture, what we call, attention layer, but what we call it as transformer, attention is a part of it. Transformer themselves, transformer architecture doesn't stop there. A transformer architecture will look something like this. Now, what I have talked in the past 2 hours is just this orange box is here. They have different layers, but luckily these layers are slightly easier. They have this normalization layers, and normalization layer, what they do, they normalize, Z normalize per feature. Like if you take this, like imagine if you calculated, you get here, if you have a matrix like this, if you want to do Z normalization, you take each feature, you calculate the mean and standard deviation, and then you Z normalize it. Then the normalization layer, one thing it will do a Z normalization across the features. We like normalization, scale them down based on the changes. But one thing also does, which is again counterintuitive, is it brings this residual connection. And these residual connections are interesting sort of, again, dimensions to these models. A residual connection is a copy of the input comes back here. You've done all this to let your model to learn the self-attentions, all these complex combinations. And then once you've done that, again, you're adding it with the input itself. You're just reminding your model, this was your original input. Heuristically, apparently, it's better to help my model to still not to forget the original data, and improves the sort of the power of sort of predictability of the model. And we have 2 residual connections in the attention architecture. One will take directly from the input itself, and one will take it from output of this here. And each of this goes through, again, a parallel neural networks. You run that results of this normalized, you do the attention, you do all that sort of residual addition, you do normalize it, and then you feed it to a fully connected network, but you run several of them. And then you take the result, and again, you take the residual, and you apply it to another normalization, and that will give you the output. I've shown it mathematically here. You have an X. What you do, you are multiplying the X. This is here. This is X itself here with multi-head attention, which comes from here. Multi-head attention, which comes from the results of this, and you create the output. Then you take that and you do a normalization on it. And then once you have done the normalization, then you apply each of these XNs to multi-layer perceptron models. Now from here you have activation functions. From here you have now activation functions. You feed it to multi-layer perceptrons, then you get that, and then you run it through again a normalization layer, and that becomes your output. That's the full attention is you need architecture for a transformer model. That's just one transformer model.
How deep are these the parallel neural network part?
I think I have some statistics. I'll show you what ChatGPT uses the parameters. Again, that's what I'll have some numbers. Specifically, I looked at GPT-2, to be fair. I didn't look at the others, but I have some statistics that will show.
But like, what's the most expensive part of that network to train? Is it that final parallel neural network? I guess it must be.
In terms of the computation, it's I think if you don't have activation, a lot of up to here, a lot of it's just linear transformations. But once you get to that, and then you have activation functions, and then you need to calculate the gradients, I think the parallel network's probably computational a bit more expensive. That's also my intuition behind it, because the others are, you can done it in parallel.
Yeah.
Interestingly, because there are parallel networks, also you can train them in parallel, but still there are complex networks to train. And all that, when you say complex networks, is just because the way the neural networks are trained, you run one step or you run a batch. Usually you don't run one step, you run a batch, and then you calculate your error and you feed that error back through all the entire neural network. You update the weights and you repeat and you repeat and you repeat until your network converges. I took this, if you've come across, there is a company and a website behind it. It's called Hugging Face. Have you seen the Hugging Face? People put the pre-trained models. And I took the transformer example. In Hugging Face, if you just search Hugging Face transformer, you will see a bunch of transformer models are there. I took just one of the standard ones they had. And I'll just show you some examples how a transformer trained works. This is obviously a transformer. I didn't look at what they had. It probably is trained on Wikipedia. Is not as good as ChatGPT, and you will see how they work. In this case, your model doesn't predict one word. It predicts a series of words. Like basically, it depends again what you train it for. You train it to do a sequence prediction. And then you start writing it. I've started writing it. What should I do to become a neuroscientist? Yeah, that's what the question I ask. And the model starts giving some suggestions. In this case, the reason I took this, because this works like ChatGPT, but it shows you the suggestions and then you can choose it. And imagine each of them internally for a model will have a probability. Yeah. Something like this. Probably the other way around, because the higher probability should appear first. And there will be lots of other suggestions your model will have, which doesn't show it here. This case shows the top probably 3 ones. In reality, as I said, the large language models, in reality, just the sophisticated ones like GPT, they won't show the top probabilities because these probabilities could be very small. They will choose the top n, and from top n, they will just give you a suggestion of the random. We will pick one random one and they move to the next one. And each one will give the context to the predicting to the next one. And you can see the predictability and unpredictability of this, depending on how you train. The whole thing is a heuristic model and based on some probabilistic inference behind it. And let's start writing a novel. My story begins on board of a ship to Antarctica with captain, and then it starts looking at what has come across, like what seems to be better context for this. And a crew of an American research ship. Probably my feeling is these are one thing also you have to be the reason I chose it. I remember these could be also the models if they are not trained carefully. Maybe this is actually plagiarizing, not, I mean, consciously or unconsciously. Actually, they're taking the entire syntax from a text. It seems to me it just could be just a syntax from somewhere. I haven't done a Google search, but the GPT type of models are much more sophisticated than this. I just wanted to show an example of internally, GPT will have that. It just doesn't show it to you. Internally, it does it once it goes under time, quickly produces. You say, write me a proposal on this, or write me my essay, or something like this. In a second, it creates it. In reality, in the background, runs this process constantly, and might be at some point gets to a dead end and goes back and retracts it and revises it. The GPT type of models, they will have more sophisticated data engineering and information engineering behind it to create more plausible set of sentences. Does that make sense? If you use a series of probabilities, you might just go to the end of sentence and calculate if I went through multiple routes, which of them would have eventually would have created a higher probability, like just relying one probability at a time. Those type of inferences can go into these models to improve them. But in principle, they will start with the process of tokenizing it. If you have a natural language, if you have a text like this, you will start just creating the tokens first. You just separate the tokens. And then you start, once you have done the tokens, you start thinking of how I should represent the tokens. Inevitably, some of the words when you do tokenization won't be in your vocabulary. And depending on, again, what you want to be sensitive, like the sophisticated models will look at each of this as a separate word. You embed them separately because you want to be able to predict them separately. They each will have their own tokens and different versions. And you can guess why now models like ChatGPT get the grammar right, because each of them grammatically also have been tokened separately, because the model has learned them separately rather than trying to embed the grammar later. And you think, why always gets the grammar right? Because it's looked at a lot of correctly grammared sort of text and has embedded those words separately. Does this make sense? Gradually, I hope some of this, again, if you leave this and you thought, first, I hope you don't think you wasted your time, but if you think I learned 20% of what you said, probably is more than me. And then what we do once we have learned the tokenization, we have created one hot encoding. Imagine here our x-axis will be all the vocabularies we have in our language model, whichever we are using for. For example, if you take Wikipedia, probably you will have something around 30,000 really words. It depends again how detailed you want to do this. And then they will have one hot encoding, means each time a word appears, you just make that on and the rest are off. And that calls one hot encoding, and that will create a representation. And then what we do, we take that and we create a embedding, like sure that a way of word to vector representation. You apply one of these word to vec models and you create a representation. A typical representation, for example, is dimension is 1024. Means your word is represented by, so far all my examples were 3 or 4 dimensions. In reality, you have 1024 dimensions in your model, and you will have something like 30,000 in your vocabulary. Imagine now if you're predicting the correct word, your class you are predicting has 30,000 members. If you have worked with neural networks of trained any machine learning, usually you rely on what is the highest number of classes you have trained a model for. If you have worked with CIFAR 100, probably you have created for 100 classes. Like CIFAR 100 is one of the benchmark imaging data, has 100 classes. Have you trained for something larger number? If you have used MNIST, how many classes you have? 7, 8, 9? 10. MNIST has 10 classes. CIFAR 10 has 10 classes. Or most of the time, the classification problems you're working like they're like 2 classes, binary, 3 classes. Here you have, if you're predicting a word, 30,000 words to predict. And you can see the probabilities can be very, very small. That's again, that's why the people take the top n and they use a random selection of them because they don't want to rand. If you're looking at this, read it from this side to this way. I know it's shown a different way. These are your one hot encodings. These are the embeddings you have learned through a word to vec. Imagine that you will have a word to vec mechanism, which is outside a attention model. You're learning how to represent them, embed them, and when you learn the weights, each word will be represented by an embedding. Here we have taken I don't know how many dimensions we had here, and the representation embedding we have is 1, 2, 3, 4, 5, 6, 7, 8 dimensions. Yeah? They are represented each word with a vector of 8 dimensions. And then we can apply in a sentence a positional encoding. Once we have that positional encoding, it's really, really simple. Like a few lines of code, you can do positional encoding and you add the positional encoding. Once you have the positional encoding, actually, you don't need to forget all I said about transformers because they will be existing models. You can, in PyTorch, you can just call a transformer model, or in Hugging Faces, you just feed the information. In a lot of time, when you're training the transformers, getting your input to the right format and understanding how the model works is important. But all I said, you can then ignore and just see how you do the embedding and how you do the positional encoding. The rest, you can use the existing codes for a transformer and run it. You don't need to encode everything. But in reality, the transformer models, how you train them now, you're trained on a variety of tasks. You can create like, there are different, there are 3 typical types of transformers before I go. An encoder transformer, which transforms a text to a representation, and then use it for a variety of tasks. For example, so far, most of my example focused on this part. I just showed a transformer encoder. You encode it, and then the tasks you are using for, what people are training this for, they will give sentences, and as I said, mask a sentence and ask the transformer to predict that sentence. Word. In a sentence, they mask a word and predict that word. They give reviews, and they ask the transformer to predict whether this review was positive or negative. By doing that, the model starts. Basically, you can train your model. You need some function to train your model, and those are the training. A decoder generates a new token and continues the input text. This is the GPT form. These are generative pre-trained transformer. You train a transformer, and then you train it to predict the next word. And then you measure how good or bad it was. You need to have a function to train it. You need to have a way of training it. And training it here, you will mask the word. You will give a Wikipedia sentence or the word of following sentence, and you ask the model to predict. And based on what it predicts, you measure the error and you train the model to predict it correctly. Does that make sense? And if you have used Bayesian models, has anyone tried Bayesian model? This would have been similar. If you wanted to do Bayesian you would have had Gibbs sampling, a conditional probability of giving x and x1, x2, x2, x3, how I'm predicting my z1, and now giving z1 and x1, x2, x3, x3, how I'm going to predict. And imagine if you did Bayesian, this becomes just mind-blowingly. I can't imagine how you could do it. But heuristically, the attention models can do this. And there are also encoder decoders are used to sequence translation. They use, for example, translating from I don't know, English to German, German to French, and this is like how Google Translator and lots of other models work. Basically, they use the translation. I'm not going to do the discussion. There was a study, again, I came across a couple of days ago from Stanford. They were saying some of this, people say we have trained a lot. Like there was a discussion at some point, I think it was Google or somebody said they have trained a large sequence to sequence translation task. They said we never trained the model to translate Bengali, and the model now being the Bengali text, it actually translates it. And I don't know if you come across the discussion of saying, have we created something which has minds of its own or can train itself? And there was a paper, I think it was from a group in Stanford, they were arguing maybe actually there is something within the model design has created it. And now with all brief things I've said, you can imagine if you word embeddings actually for Bengali and like, let's say Hindi or I don't know, other similar languages were very similar, you might have trained your model on Hindi. And because the word embeddings are so similar, you might just get Bengali and you think I have never trained it, but because a lot of architecture and a lot of word embeddings are similar, you model actually might be able to reasonably well predict it. And a lot of discussion depends on what metric you're using to predict it. Then what I'm saying, a lot of this perceived as artificially like sort of above human level intelligence, you have to treat it very, very carefully. I'm not saying that you're not capable, just saying you have to think now, understanding architecture, where that actually comes from. Was the word embedding of the Bengali was very similar to another language they had trained it for. But generally they are, I mean, I don't need to explain that you have seen the language-to-language translation, how they work really well. BERT is one of the early models, which was a large language model. It started with vocabulary of 30,000 tokens. I think it was trained on Wikipedia. They had each was converted to 1024 dimension words, means word embedding created. Each word becomes a vector of 1024 dimension. Computer scientists, they like this 1024, the power of 2 sort of dimensions. And then they pass it through 24 transformer layers. Yet then they had 24 transformers. Like, each single transformer had 16 heads. Now get your model. So far, what I've explained is one transformer. BERT has 24 transformers to start with. Each transformer has 60 heads. Multiply it. The dimension of the hidden layer of the neural network is the 4096, and in total number of parameters is 314 million parameters. This is BERT, which is relatively now simple. Yeah, this is BERT is very now a lot of language models. BERT is relatively in this world relatively old and relatively simple. And this is the simple one, has 314 million parameters. When I talk about parameters, you are looking for an optimum. At one point in between this 340 million, at some point, if you set them to certain values, they will give you the best result. And the whole point comes heuristically, you need to find a way to find where that parameter is. You will may never find the exact combination, but you can want to get as close as possible. And that's where you start training it. Encoder explores the transfer learning. Basically, what you do during the pre-training for BERT, you do a self-supervision from a large corpus of text. What you do, you use model-to-model generation. I'll say what you do with self-text generation. Do you give a sentence? As I said, you mask one word in the sentence and you ask the model to predict. Basically, you could create your own supervised task by some unsupervised sort of data you have available. It's easy to do that, right? Take Wikipedia. Each time you just mask a word and ask to predict it. There are some practical implementation issues in that, which probably I'll talk if I have time about it. And in fine tuning, what they did, they adapted to solve a particular task, a smaller body of. They also, to see whether the fine tuning works better, once they did the text generation, they're basically predicting the text. They took BERT and also they tried to train it to do another task. For example, see if a review is positive or negative. In reality, that didn't create much improvement into the model, and a lot of improvements, just training comes from just the first part of it. In the pre-training is just a self-supervision. Then what they call it is a self-supervision. Self-supervision, what it does, it predicts missing words for a sentence from large internet corpus. Again, probably when they refer to large internet corpus, they use Wikipedia often because it's publicly available. Exact, I think they have used. During the training, the maximum input is 512 token, and the batch size is 256. Again, I think the earlier question was if you have very variable length sentences, how this happens. BERT assumes your input size is 512. X1, X2, X3 goes up to X512. And if your sentence is shorter, you can obviously add it. And the batches, if you have trained neural networks, you know you don't train it, you don't update your gradients at every single input. You just take a series of inputs and then you calculate the gradient, average gradient, and you update your network. And that happens for every 256 inputs in this case. They trained the BERT initially, when they trained it, roughly 550 epochs, means the model saw the entire text corpus, the entire data set they had, the model saw it 50 times. And the word size for this was 3.3 billion words. You get the scale of, even if you want, this is a very small, and you see why everybody wants GPU. You can see this scale of this. And in reality, BERT, again, uses word embedding first, and the word embeddings create 1024 representations, and then has, how many transformers I said, has 24 or whatever number of transformers this has. And then each of the transformers, they have 16 heads, and you apply it, and then you have a linear softmax layer out of it, and then you're predicting these missing words. Does this make sense? It's trained like that. There are different variations of BERT. A group a few years ago, they took BERT and they trained it on publicly available electronic healthcare record data from Mimic. If you're familiar, Mimic is a publicly available electronic healthcare record data set. And they used this Wikipedia trained model, fine-tuned it on electronic healthcare records, and they call it MedBERT. There is a BERT version, it's called MedBERT. Now, you might just take BERT, for example, and I don't know whether it works with genomic sequences because there's not much similarity between sorts of Wikipedia text and genomic sequences, but there are different versions of this type of BERT models. Predicting the missing word has a problem. If you're for example, obviously, if you try to predict before I go to the problem, if you're trying to predict the missing words, you will say, for example, red always appears with house and car, but never appears, for example, with shout. You just with the self-attention and all this training process, basically that's what model lacks. And then you input to the model will be something like this. You will mask this input, and you let the model to predict the word. And each time you mask one of the words. The problem is because you train them in parallel, you train them all in parallel. The problem is if you suddenly in parallel, you give the sentence, and each time, each of these layers, they see one of the missing words. In reality, you might just leak the words to one to the other. And there are some engineering ways of how BERT is trying to avoid it. But as I said, BERT tried to give a secondary task, which predicting two sentences were originally adjunct to each other. BERT was trained not only just predicting missing words, also to see whether it can predict what would be adjunct sentence to it. But in reality, it didn't improve much of the task. Yeah, as I said. That's when you take the now BERT and you're fine-tuning with a particular task. Basically, you train it and then you give it another task, and your model parameters already trained in the first task, and then you give the second task and you keep the parameters you had learned from the first model, and you just start updating the parameters. And in this case, what they did in BERT, they gave it in fine-tuning, they gave to predict the type of entity, whether this is a verb, whether this is a noun, this is an adjective. And the first one was predicting missing words. And then once they train them, complete the entire training with this based on 50 epochs or whatever, 360 million parameters they trained it, they started from scratch with another task. This time, but they used the already pre-trained parameters and they trained it. And you can imagine even BERT is simple, there's a lot of training has gone behind it. Does that make sense? Now the GPT,
So each transformer block is a multi-head self-attention plus the parallel neural network. And then you just copy that, you stack that in series multiple times.
in parallel, not in series, not sequentially, in series, in parallel.
Each transformer block is in parallel. Okay.
I think so.
A transformer block.
Oh, sorry, no, yeah.
Yeah. It's a-
Each of heads are in parallel, transformers, yeah, transformers are sequential.
But the heads are all within one block, right? So
Each block has 16 heads.
yeah. Okay.
Then you will have like, how many blocks we had? Let me just go back, I remember correctly. BERT has 24 transformer layers, 24. Then here you have 24 of this. This block is repeated 24 times.
It's like nothing like how the brain
No. Absolute, like it's a very it's complex.
Anybody saying that these things are conscious, it's just like insane.
The only thing is they create models, then at some point the model does a task, they can't even explain themselves. And as I said, the recent study was saying probably they get carried away by how they interpret this. I totally agree. But once you created such a complex architecture, it becomes very, very difficult to trace it back, what happened. And as I said, the Bengali translation was an example of it. Maybe actually technically makes sense. To me, actually, if the word embeddings were similar, as I said, probably makes sense. But suddenly people get, oh, wait a minute, this maybe has its mind of its own and does this translation. But again, you can imagine how computing world in a matter of like for years and years, AI didn't progress much. Like when I was a student, AI was pretty much the progress was incremental. Suddenly in a matter of like, since the deep learning models and the computation power is allowed to create these models, because these models in reality are all based on just some neural networks. It's just, and we had this, it just because the computation power allows us not to create much more complex models. And we have a large, like Wikipedia, I don't know, large data sets. It's just suddenly given sort of opportunity for people create a lot of very complex architectures. Again, whatever we think about attention model has changed AI massively. This probably, if I don't know, I'm not the right person to, but if I pick up one sort of seminal work and say this has massive as an influence in AI in recent years, is probably the transformers. As the look at just GPT type of models and things. And tomorrow I talk about variational models and diffusion models. They are another sort of madness in their own world, how they work. But in reality, you will see how they compare with the transformers and how transformers are constantly used. But a lot of it also goes back to Greg's earlier point, say, did we really need it? Do we really need all this complexity? Do we need this old 16 heads? Do we need all the 64 blocks? People added it because they could, and they had the computation power added, and they got better results. But to what extent this results can be improved with much smaller models is yet to come. But I've seen some recent works suddenly with a scale of 1,000 times of smaller parameters, they create similar results.
But new low rank models, though, are they actually trained on small architectures, or is it just that you learn these very high dimensional models and then you trim them by like doing redundant?
My feeling is a lot of them, they learn the high dimensional and then trim them down, or they might use the results of this to train something like probably they might use BERT to train another model. Yeah, which exactly becomes trimming down another model. But take GPT-3. GPT-3's basic architecture is very similar to encoder model and uses a transformer. You have lots of architectural things to decide. For example, full stop should be added as a token because our model has decided at some point to put a full stop. Probably these are the type of things. Where do we start? If somebody write me a resume for a, I don't know, software architecture who can get a job here, the model generates you this resume. Where this comes from, where we should start. Basically we need to give a lot of this. There's a lot of information engineering behind it because you need to start from somewhere. GPT doesn't show all that to you. It just shows you the sort of curated result in the end. But in reality, a lot of it just relies on transformer models. And as I said, it just take BERT. And if BERT uses like 24, 64 of these blocks, imagine GPT uses much, much larger models of this. And in reality, what it does, if you wanted to create it, this is the Bayesian version of it. Like if you wanted to create a conditional probability, if you wanted to say it takes great courage to let yourself appear weak, if you wanted to do probabilistic, this is a conditional probability. You predict the probability of the first one, probability of the second one, giving the first one, and so on. This is the conditional probabilities. And there are, in Bayesian world, we use keep sampling and different ways of learning this. But you can imagine this becomes a very complex task. GPT is an autoregressive model. Basically, what it does, calculates the first probability, giving the first word, predicts the second one, giving the first two, predicts the third one, and so on. This is the same concept we're thinking in mathematical world, right?
What's the order?
The first one you predict PT1. This is the P token 1. You predict the P token 1, and then you predict the P of token 2 given token 1.
So this is order 1. So it's always given the previous.
Yeah. This is just the base.
Just one, which is the previous.
Conditional probability, and given the first two, predicting the second one.
Wait, so the order increases as the sequence goes on.
Let's say the token one it just has probability of T1, right? Token 2 has probability of T2 given T1 in a sentence.
And then T3 given T2.
Token 3
Or given T2 and given T1. So the order increases by 1 every step. Doesn't that mean
it's a conditional probability.
Doesn't that mean that it gets more expensive to compute as you go through the sequence?
In a Bayesian world, this is writing in a Bayesian world. Yeah, but in reality, yes.
Okay.
Yeah. But what you do if you're predicting this, if you want to create a sentence, each of the next appearing words, it depends on what you had written before. There's a conditional probability in a sentence, right? That makes sense? GPT that's creates basically the whole text GPT writes for you. It has calculated what was the probability. If I said this, what's the probability of the next word I'm going to say?
Surely it must have some short-term memory. Like, how could it just be? Otherwise, as the text gets longer and longer, then surely it's just getting more and more expensive to compute.
Good point. I'll come back to that in a second. That's a very, very good point.
Yeah, because I was going to ask, like, if we then have to also link in some of the previous sentences to try and get the probabilities down the line to create your whole paragraphs.
Both are very, very interesting questions. I don't know how GPT does this, but I'll tell you how you can do this. You might just finish a sentence, predict the sentence, and start a new sentence, right? You just finish a sentence. And yeah, as you said, if you're predicting the entire text, you start the first word and the probability of the first word in the end word, you add all the probabilities, becomes very complex calculation. If you're using transformer, you've already calculated the self-attentions, and you use those self-attentions to predict. But in reality, what you might do, you might just, as my example from Hugging Face, you might just not predict a word. You might just predict this sequence. Then you do first more than a word prediction. And if you do a prediction of a word, you might just have like sliding window. For example, when your sentence finishes, you might just give the previous sentence and gets given the previous sentence and this with the next word. Or depending on how much complexity you add, the further you keep in memory, the further complexity of the conditional probabilities are. But in reality, that's what you do.
Doesn't the self-attention part already have this autoregressive property? Because like the output of that, of the softmax, is essentially a conditional probability. What is the likelihood of me observing this word?
That's correct.
So
that's correct. The way this is shown as an autoregressive language model, this doesn't reflect the transformer architecture. This reflects the
Yeah, I think you're just describing a kind of property of the model rather than.
Yeah, the model itself. Yeah, this is not the model structure. This is the property of the model. The model will give you those probabilities. But the only thing is still you need to make a decision with all this, to what extent you're going to involve the previous ones to predict the next one. Yeah, it still is a decision you make. Yeah, this is the property. With all the attention I said, it comes down to you don't want to calculate those self-attention those probabilities, because if you could calculate those probabilities in the first place, you didn't need all those self-attentions. They will calculate that heuristically for you. One thing I just wanted to say, if you're creating this parallel because you want to train this parallel and you want to mask different words, and if you're training it parallel, as I said, you might just keep the information, leak the information to the model, and model might just basically cheat because just has seen the rest of the sentence in other sort of outputs because you're training it all the same time, right? then there is a way of doing this, which the model, if I'm not forgot, let me see how GPT does that. Do I make sense in the first place? Where is the problem? You're creating these parallel lines here, and you're masking one word of a sentence, the same sentence, you're masking one word of a sentence, and you're giving the model to predict it. Because you're at each point of each step, you're showing part of the model. In the end, actually, the model might just see the whole sentence, because if one tail doesn't have, the other one has it, the other one has it, and change it. I've forgotten how GPT avoids that, but has a function which tries to, what you call it, mask self-attention. It does. Let me remember. I can't remember how it does, but has a mechanism which makes sure the this mask sort of when it does attention, the information doesn't link across the layers. Do that make sense? But I can't remember how it actually does. I've forgotten this part. I hope the problem at least is clear. If not, then what happens is in Decoder, what you do, you take now the vocabulary of you apply all this. Sort of you do this all this encoding, and you create the transformer representation, and then you have a function. You want to basically see what the correct prediction word is, what the missing token is. You apply a softmax, and you take the result of that softmax, and you say that each head predicts the correct word, and then you update your network based on the sort of the error of that. Is it clear? Now we are getting to how we're predicting. But imagine, because we are giving this parallel, we are giving a sentence, and each of them will have a softmax. Each time, each of those heads will predict one word of the model. Predict Paddington. The first one will predict Paddington. The second one will predict whether there's vent. Third one. You're just training the model in parallel to help the model to basically computationally to improve it, rather than sequentially just creating an each input. You're just training it. This is in parallel. GPT-3's decoder layer does that. One thing, again, I can't remember, is does something is called mask self-attention to make sure, because you're giving the sentence across all those layers, all those lines in parallel. If you look at all that, the model has seen the sentence all together. It just has a trick which allows you to, it stops the model to sort of leak that information. As I said, in autoregressive models, there are a few things you need to decide. Where is the starting point? How are you going to create the starting? In ChatGPT, you write it sort of a chat query and probably uses it to create the first word. Once creates the first words, can get going or creates it. But as I said, the results you see from ChatGPT or those information are taken out. They don't show you. They just show you the curated result. Does that make sense? In autoregressive language, when I say, I don't know, write me a proposal for applying for a neuroscience fund, it will give me the text. Where should be the first word? That first word probably is created based on my query, but the model just doesn't show that. As I said, a lot of this regressive models, this information are not shown. As I said, again, I've repeated this, for some computational reasons, and because the probabilities are small, the model rather than choosing always the top result, we just choose, we list the top k results and randomly choose one. This is for just to stop the model going to a dead end. My feeling is, if I were designing something like this, also I create a sentence, and then I try to multiple routes to see which combination would have given me the best results rather than relying it. But I don't know GPT internally how it does that. But GPT-3's scale, now we have GPT-4, is that correct? GPT-3's scale is, the tokens here are encoded in 2048. This is twice the size of BERT. You see the embeddings are now that become 2048. And the batch size is 3.2 million tokens. Each batch you give 3.2 million tokens, and it has 96 transformer layers. There's 96 transformer layers, and the word embedding size is this. Each transformer has 96 heads, and the query key dimensions are 1 to 8. Olivia, this is your earlier question. They have changed a different dimension they use for the value key query. They've trained on 300 billion tokens, contains 175 billion parameters. This is GPT-3 for you. In reality, it's just the transformer we looked at today. It's just a large number of them. But in reality, the architecture is largely the same. I'm not saying the entire work OpenAI has done is just goes down. It's just very largely uses the same architecture. I hope it makes sense. Now, why people are talking about the computational problems of this and how complex these models are. And as I said, this is GPT-3, but you can see also because they are trained on existing languages and they have learned all these embeddings and all these attentions, they are also hugely unpredictable in things they haven't come across before, in things like, or hugely also dependent on what they have been trained on and how they have seen it. They have never seen read and shout together, but they have always seen read and train together. Then they will give more self-attention to that. And that probably when you read now the abilities and sort of limitations of this model will give you some clues of what are the model's limitations of this. And as I said, the other type of transformer you can use it is encoder-decoder example, which you give sequence to sequence. You give just for machine translation, and you have all come across it. We use it constantly. But what you do, your model now, rather than just predicting one sequence, uses predicts another sequence. Interestingly, like to translate between English and French here, what you do, you create a transformer block. And you do all the embedding and everything for transformer self-attention and everything for the English one. And while you're training your now large transformer for the French one, what you do at some point, you're giving the mass transformer information from the English one. Basically, you are still training your French transformer to predict the missing words of French. But while doing that, halfway through, you're also feeding the English words embedding into that by the transformer. And that's sort of then you're learning, if I gave this English words, what would have been the French word? Makes sense. I hope it makes sense. It's just, again, just this how you put these models together. I mean, with the hindsight, it's, oh, yeah, why I didn't think of that. Well, it's very, very clever how they train these models. I don't know what would be neuroscience equivalent of that. And that's called cross attention. Basically, now you have two attention models. You just add a cross attention from one to the other. As I said, here you're learning you're still predicting the missing French words, but at some point you're adding the embedding of the English words to that, and that's called cross attention. Again, the cross attention architecture, you have the same typical design, but here some of this comes from another attention model, obviously added to this. Yeah. The rest architecture follows the same. I'll talk more about this later, and this would come once I also talk about the diffusion models, but I wanted to say all my examples today relied on natural language processing, but the transformers also apply to images. And in fact, you can use the similar concept here. Probably creating embeddings are easier relatively because the images are sort of coming in vectoral form. And what people also do when they create the transformers based on them, also they condition it based on a text. Now, when you have images, you have thousands of images, of millions, not thousands, millions of images you're giving them, and also you're giving text what is in the image itself. And then you learn the transformer. What it happens, the side product of it becomes next time when you say, I want a cat flying in a blue sky, the model will pick up first cat and blue and a sky, and we'll look at all the embeddings and encoding as learn, and will become, because it's similar way you were generating text, you are generating now basically tokens for your images, and you put all those tokens together and you make up an image. I'll talk a little more about this probably in the next coming days. But Google Research, again, has a work on this. It's called Muse. And at the moment, this outperforms what they all the benchmark generative models on creating images. They create really high quality. If you look at the website, they create really high quality, real looking images, literally by just typing it. I'll talk more about this, but you can imagine they divide the images to little mosaics and at different resolutions as well. And then they apply all the self-attentions to models. And what model learns, it learns these little blocks and then learns what could be next to that block, what most likely to come to the next block, condition to what you're looking for. And based on that, they will create high quality images. But imagine if you take the entire world and think everything is fractal, and you learn those fractals and you learn how the combination of fractals can create. Heuristically works. Technically, you can imagine how these are designed, but when I say the product still is mind-blowing. I'll stop there. I've already exceeded my time. And if there were any questions, please write to me and I'll try to give my best answer as much as I can. I have uploaded this on our GitHub page and I've uploaded a very simple code from PyTorch. I just took PyTorch's example, but made it run a transformer. If you look at Hugging Face, there are examples of a transformer, pre-trained transformers. And also I put an example of how you can use OpenAI's GPT. Relatively simple. It will take you 5 minutes to actually use GPT's API, OpenAI's API to use GPT, to basically ask GPT to give you response. What you see on ChatGPT, you can add it to your program. The only thing is proprietary, is not free. If you create an account for 3 months, you get some tokens free. After that, you start paying. But there are a lot of different, if you see applications, they use GPT. I just wanted to say it's relatively simple. It's very simple, not relatively, it's very simple to actually to add that to your programs, to your systems. And there are also lots of these pre-trained models. You can take it and train it for other purposes. As I said, BERT has been taken and trained for medical data. It's MedBERT. I've seen people working on the genomic side of it. You can take basically the existing models. And interestingly, sometimes the cross-domain, which sometimes doesn't make much sense, but it seems to work well. Like if you're training it in another domain, sometimes it seems like even taking from text, still the model has learned some relationships, which is useful. Just have a look. Thank you very much. I'll stop recording. And I find a way to put the recordings. Last time I asked the college, they said there are GDPR issues, but this time I didn't ask them, then I can put it somewhere. I'll find what is the best way of it. Tomorrow I'll talk about variational to encoders. That would be less interesting and more boring though. Okay, I'll do each of the teams if there are no further questions.
Thanks very much, Ryan.
No, you're welcome. Thanks for coming. I hope it was a good use of your time.